To see why we need another comparison test beyond the direct comparison test, let's look at another example. So let's consider the sum from n equals 1, or let's say n equals 5 to infinity of 1 over n squared minus 2n minus 2. So it looks a lot like the one that we looked at in the previous video. The only difference is I've changed the signs of the numerator. And you may want to compare this to something like the sum of 1 over n squared for exactly the same reasons as the other one, that when n is large, the n squared is going to be much more substantial than the other two terms, and so it would be reasonable to hypothesize that the 2n and the 2 won't really matter a whole lot. However, let's notice if we call these first terms an and the terms in the second one bn, that if you were to graph these, you will see that actually bn is less than an. All right, let's actually check that. Let me bring up Desmos again. So I'll change our function here. So an now has the negative signs, and we'll go from 5 on. And so you see that the green series is now the larger one. Oops, let's put a minus sign in there so that looks more correct. All right, so the green series seems to be the bigger one, and that was the ANs. The purple one, which was the BNs, is smaller. Okay, so what does that tell us? Well, if indeed that's true, and they're both, of course, positive here for sufficiently large n, that means that the sum of the BNs must be less than or equal to the sum of the ANs. And we already know that the sum of the BNs, 1 over n squared, is a convergent series. And, well, what this means is that the sum of an is bigger than something small. And by small, I mean it's finite. It doesn't add up to infinity. It adds up to some finite number. And unfortunately, that doesn't tell us anything. 10 is bigger than something small, but so is infinity. Both of those would be bigger than something small. So you could either be finite or infinite, and both would be consistent with what we'd observed. So this is what we would say is an inconclusive test. Inconclusive. And that would be a reasonable thing to conclude when you have something bigger than something small, or equivalently when you have something smaller than something big. And again, I'm using big and small as shorthand for convergent. Small means convergent, big meaning divergent. Okay, so the direct comparison test fails us. You could try another comparison, but it's going to be a little bit tricky to find the right thing to compare to where we can still actually determine what the thing we're comparing to actually does. All right, but that original intuition that we had, that these two series should behave the same way, since for large n, the denominators are not going to be that far apart, it seems like that should still be relevant here. Doesn't it seem like they should ultimately both converge? Well, how can we show that? Well, that brings up the next series that we need. It's called the limit comparison test. And it says the following. Let's suppose that we have two positive series, an and bn are both greater than or equal to 0, and that we can evaluate this limit of an over bn from n equals or n going to infinity. In other words, we can look at how big are the terms, or what's the ratio of the terms in the two series when n is large. And let's call that answer L. And what the limit comparison test tells us is that if L is some positive finite number, then the sum of an and the sum of bn do the same thing. In other words, both converge or both diverge. Okay? All right, so let's try that here. We would like to look at the limit as n goes to infinity of an, which is 1 over n squared minus 2n minus 2, all over bn, which was 1 over n squared. And we could simplify that limit just a little bit. We could multiply by n squared on top and bottom. And we would get just n squared over n squared minus 2n minus 2. And that looks a little better. It's still going to have the form that's indeterminate. Before, we would have had 0 over 0. Now we're going to have infinity over infinity. But you could apply L'Hopital's rule here, or what I prefer to do is let's divide top and bottom by 1 over n squared. We'll be left with just 1 on top. And on bottom, we'll have 1 minus 2 over n minus 2 over n squared. And notice that as n goes to infinity, those last two terms are both going to approach 0. And so we're going to get 1. And we will move that camera out of the way so you can actually see that last bit. Okay. So we got a ratio of 1. And what the limit comparison test tells us is that since we got some positive number, that both an and bn must do the same thing. So that since we already know that the sum of 1 over n squared converges, we can say that the sum of an converges as well. All right, so the limit comparison test works out really well if you get a positive answer for that limit. Obviously, we have to be able to evaluate that limit, so if the limit is too hard, then that could be a problem. But for many cases, we will be able to evaluate the limit. On the other hand, if you get 0 or infinity, not all hope is lost. In fact, the limit comparison test can help us in those cases as well. And so if you get L equals 0, then what does that mean? Well, let me remind you, an over bn was the ratio that we're looking at. And if that approaches 0, then what that means is that bn, the denominator, was much bigger, and I'll use this sort of double greater sign to mean it's much, much larger than an. And if bn is greater than an, and we know that the sum of bn converges, well, then we're in a smaller than small scenario, and we can conclude that the sum of an converges too. Okay, so if you get 0, what it just means is that whatever you get when you sum up an, it's going to be much smaller than the answer that you get from summing up all of the bn's. And so if the bn's are finite, then the sum of the an's must be finite as well. And if you get infinity, then the opposite is true. Then that means bn is much smaller than an. The denominator was much smaller, the numerator was much bigger. In other words, if the smaller one diverges, then the bigger one must diverge as well. So these two cases are like the direct comparison test and then this first case that we saw earlier is kind of the middle ground. That takes into account the borderline cases where an and bn are very close to the same size, and we can still actually use that result to determine if a limit or if a series converges or not. Okay, So if this all feels very familiar to you right now, that's a good sign. When we talked about improper integrals, we did a regular comparison test and a limit comparison test. And so this is essentially the same idea. The only difference is instead of comparing areas under curves, we're comparing areas represented by infinite series. But the intuition and the rationale behind the test is exactly the same as before.